G'day everyone. In today's Chem Help video, we're going to look at the concept of back titrations. Titrations are a topic that instills some fear into quite a few students, but if you really look at them, they're a simple mole calculation really. What we need to do is turn the quantities we know into moles, relate moles to moles, continue the calculation through, and eventually we come out with a result. So titration is a little bit scary, but they're not super difficult. The back titration concept though instills fear and panic in lots and lots of students, and they come up in exams quite often because they're that extra little bit of a twist to the normal titration question that can just make them that little bit harder and just really push your understanding of the titration concept. So let's look at how to do a simple one and step you through the reasons for a back titration in the first place. Okay, so first of all, back titration questions. A back titration, or an indirect titration is another name for them, is generally a two-stage analytical technique. And that's the thing that throws people. You see two steps, two distinct equations, two distinct experiments, if you like, within the one question. People say, I don't know where to start, what do I do? And get totally thrown by the question. There'll always be a titration component, and there'll be another component, which is an addition component. They're usually ordered, step 1 and step 2, and we'll show you how that works. Okay, so the first thing. First of all, you have a reactant A. We'll talk about what reactant A will be in a second. And we don't know its concentration. It's reacted with an excess. This is the key to the back titration concept. It's an excess of a reactant. But we do know its concentration and volume, so we know exactly about this particular substance. Then, the next step is we do a titration with reactant C. So that's a third reactant. That's performed to determine the amount of the excess. And if we know the excess and we know the original amount, we can do a subtraction. And what we do is we can figure out the amount of B that is actually reacted with A by subtraction. So that's important. Okay, back titrations, why do we use them? All right, so the first thing, we use them when one of the reactants is volatile, for example, ammonia. So that means that it changes to a gas really easily. So if you have a typical titration where you have your flask and you're swirling it, what happens is that agitation will change the volatile component from the liquid form or the dissolved form to a gas, and we lose moles. So that's not going to give us a very good result. The other time we use it is when we have an acid or base is insoluble. So for example, calcium carbonate, it doesn't dissolve. You need solutions to do a titration. So you could have a solid sitting on the bottom, but it reacts very slowly, so that's not going to work. So solids are no good. Or if the whole reaction is just too slow, as you know, when you do a titration, you need a quick result. We need to see that endpoint. So if it's too slow, it's not going to work. Or if we have a weak acid, weak base situation. Now, what we have in that place is that there's no distinct rapid change between acid and base, which gives you that point of inflection near the equivalence point. Weak acid, weak base is very slow, so the indicator will change over a number of drops, so you're not going to get your precise endpoint that you've got to have with titration. So that's when we'd also use a back titration. So here's a simple example of a back titration. What we're going to do is we're going to look at an insoluble salt. The insoluble salt we're going to look at is calcium carbonate. So a student was asked to determine the percentage of calcium carbonate in a 0.125 gram sample of chalk. So they've got a chalk from the teacher. How much of this is actually calcium carbonate? So it's an insoluble substance. It won't dissolve on the acid. We can't do a titration with it. So first of all, step 1. The student placed the chalk sample into a 250 ml conical flask and added 50 ml of 0.2 molar hydrochloric acid using a pipette. So we know exactly the concentration and volume. So we know moles. Step 2. The excess hydrochloric acid was then titrated with 0.25 molar sodium hydroxide. The average sodium hydroxide titer was 32.12 ml. So this has the basics of every back titration. There's a titration component and there's an initial addition. Now, this can get a bit more complex with the substances that are used in the examples, but the steps are the same, okay? So, you know, you might, in past exams, have had aspirin or vitamin C in this step added to a base, and then we've used acid here. But the thing is that there's always a titration and there's always an addition. So, calculate the percentage of calcium carbonate in the chalk sample that we're going to look at. Okay, so first of all, we've got to have an equation for each of the two steps in the back titration. So, hydrochloric acid and sodium hydroxide. We start with the titration, because that's the thing we know about. We know what came out of the burette and we know the concentration of that. The first step, which was the addition of the excess hydrochloric acid, we don't know enough about that. So, first of all, calculate the moles of sodium hydroxide that reacted in the titration. That's what came out of the burette. Now, we know that the concentration of that is 0.25 moles per litre and it's 32.12 mils. So we always write that underneath the substance in the equation. Then we say N equals C times V, so concentration times volume. Now don't forget, in every titration, turn your mils to litres. This is a really common mistake lots of students make, so don't do that. And we come out with a value for our number of moles of sodium hydroxide. That is how much came out of our burette. All right. Now we need to relate it to what was in the conical flask. So from the equation, we know that sodium hydroxide to hydrochloric acid is a 1-to-1 ratio, don't we? Okay, so hydrochloric acid. Now that's the excess. That's what's left over after the first step. That's the important thing you've got to try and think about, is that this is the excess. Is equal to the sodium hydroxide, so it's the same value, 8.03 times 10 to the minus 3. So the titration tells us how much hydrochloric acid was in excess. That's the purpose of the back titration. Back titration determines the excess. Remember that. Okay, so now we know the excess. We can now move towards figuring out what actually reacted. Okay. So the excess, just to restate, is how much hydrochloric acid was left after the chalk was reacted. Okay, so now we want to calculate the total moles of hydrochloric acid that we started with. That was how much was initially added to that chalk sample that the student had. So we added 50 mils of 0.2 moles per litre hydrochloric acid. So N equals C times V again, don't forget that volume thing, always make sure you change it. 0.10 moles. That's how much we actually added. We added way too much, which is good, because we wanted to make sure it was a complete reaction of the chalk, not of the hydrochloric acid. So this is how much we have in total. How much actually reacted? Okay, so to get that, this is the important bit of the whole back titration calculation. We take the number of moles total, that's how much we added, minus the excess, which we determined from the back titration itself. 0.010, that's the number of moles there, the 00803, that's how much the excess was. That number, that's how much hydrochloric acid actually reacted with the chalk. That's the key to these whole questions. That's the important thing. Right, now we know that, we can figure out how much calcium carbonate was actually in our chalk. To do that, we need our second equation. This is another thing that throws people when it comes to back titrations. Two equations, what do? Do you put them together? No, keep them as separate. Separate processes. Don't ever combine equations in separate processes. Right, so calcium carbonate, hydrochloric acid, salt plus water plus CO2. So, we know from this equation that the calcium carbonate is 1/2, unknown over known, times the number of moles of hydrochloric acid. So, put that into our calculation. 1/2 times the value of the reacted amount from the previous slide. That's how much calcium carbonate we actually have in our sample. Okay, now the sample is not pure, so that's what the percentage purity thing is. So what we do first of all is work out the mass. So the 9.85 times 10 to the minus 4 times the molecular mass of calcium carbonate. Now be careful adding those up. It's a really common thing people do wrong. Slip on the calculator, so double check if you think you need to. 100.09 grams per mole, 0.99 grams. That's the amount of calcium carbonate that we have in our chalk. Right, so now we need to figure out the percentage purity, which is what we're really looking at. What's the percentage of calcium carbonate in our chalk? Simply, it's the mass of calcium carbonate divided by the mass of the chalk times 100. So it's a 0.099. There's our initial sample of chalk that the student threw into the hydrochloric acid at the very beginning, times 100, 79.2%. That's how much calcium carbonate was in the chalk. That's a back titration. Just remember, 2 steps. Do the titration step first. That is what came out of the burette, determine the excess amount. Then go to step 1, figure out how much you actually added. Take the excess from the original, gives you the reacted amount. Then you can relate it with moles from an equation to the substance that you're interested in, and then you can figure out mass or percentage or whatever quantity you need to after that. I hope that's helped you out. Good luck with back titration.